Hello and welcome back to the crash course. Today I want to talk about exponential growth. It's a topic that is crucial to understanding what's going to happen with COVID-19, and we're seeing it in the news quite a bit. We're seeing it all over the website. It's the reason we're social distancing and why the country is locked down right now. But I think a lot of people probably might think they know what exponential growth looks like, um, and how to model it. But I think that a lot of people will find that they actually didn't know that. This is just from my experience as a faculty tutor, tutoring math for a number of years. But let's get into it. Hopefully, even if you do know what exponential growth looks like, this will be a review, or maybe you'll learn something new. Um, there are a number of different growth patterns that we can look at, and they're all useful in their own way. Linear growth is one, geometric growth is another, exponential growth is another model. These are three of the most common ones that I've run into, at least. And we're going to look at a comparison, but first, I think it's important here to review how to graph things and what we mean, because this is something that I think a lot of us forget if we don't do math for a while. So if we have a graph, we're going to have an x and a y-axis. We could call them whatever we want, but these are the conventions. The x-axis is typically our independent variable, the y our dependent variable, and this just means that y depends on x. So that when we put little tick marks in here, we could call these 1, 2, 3, 4. We can make them whatever we want. These don't change, but they will dictate what y becomes based on our model. So if we have, say y equals, sorry for my handwriting here, y equals 2x, then when we have 1 for x, 2 times 1 is 2. So we can say, okay, there's 2, and we put a little tick right there. 2 times 2 is 4. Let's try to make these kind of even, and we put it there. 3 times 2 is 6. So again, kind of plop that down. And we should end up with a straight line, right? Because this is a linear, and that's where the name comes from, right? Growth model. And if we draw a line of best fit, it should go right through. And if these were the actual data that we had, and we were trying to predict things out or model it into the future, we could go, oh, well, when it's 10 times 2, right, that should be 20. And we'd be able to predict the future with this model. But so knowing that, let's keep going, and let's clear that all out of there. And with the linear growth model, like we just saw, each time the x value is going to grow by a constant addition of something, right? So it's constantly growing, and its slope is constant, we can say. And that's the rise over run, if you can remember that from school. And a lot of times we give that variable of slope, we give it m, right? So m equals 2 over 1 or something like that. So it grows by 2 each time. That was in what we saw last time. Here's some graphs of what that looks like. So here's y equals x plus 2, y equals 2x. Doesn't matter that we're multiplying here or adding. They're still linear. They're growing at a constant rate, and we can figure that out. So here with y equals x plus 2, every time we move over by 1, we go up by 2, right? So the slope is 2. And so we'd say m equals 2. So that's linear. And there are a lot of models out there where we can use linear growth. We come into geometric. So let's move on to geometric growth here. And this is where we start to see exponents and multiplication, where a lot of people actually think this is what exponential growth is. However, it is not. We are growing pretty fast, but it's not exponential quite yet. So let's take a look at this. And the reason we call this geometric growth is because we're growing according to proportions, geometric proportions. So in this example over here, y equals x squared, where x is growing in proportion to the square of the x values. And down, if we had it as a cube, then y would be growing in proportion to the cube of the x values. And I'll kind of try to show what that means here in a second. And you can definitely see that we're growing faster. And you can also see that if we're adding, so remember y equals x plus 2 or y equals x plus 3 would be a linear growth model. If we throw in something like plus 3, it really doesn't make much of a difference. Here's y equals x squared, here's y equals x squared plus 3. And if you look at these final values, they're really not different, right? They're pretty much the same. That's because we are growing pretty quickly here. What we mean when y is growing in proportion to the square of the x value is if we have this x squared, when x equals 1, we have 1 squared, and that equals 1. So that's this. When we have 2 squared, right, this is 2 squared, we get 4. We're adding 3 new boxes. 3 squared, right, we've got 9. And we're adding an additional 5 boxes. And we just keep adding, but it's in a geometric fashion. If we were growing as a cube, then we would have to bring this out, right? And we would have to start talking about it in 3 dimensions, right? So that's what we mean by geometric. That's why this is called geometric growth. And there are a number of instances out there where this is a good model. Yeah, so that's when we talk about geometric growth. And let's finally move on to exponential growth. And this is where we start to grow really fast. It's where we start to see this idea of doubling time. And the big idea is we're raising a variable to a fixed power in geometric growth, right? So we're doing x squared. The squares isn't changing. Here in exponential growth, we are raising, we have a fixed number that we're raising to a variable power. So we're going to do like y equals 2 to the x, right? And this is what the graph looks like. You can see how much faster we're growing. And to put this all into perspective, we're just going to do a comparison, and we are going to look a lot more at exponential growth here in a second. But here's a linear on the white line here. That's linear growth. Here's our geometric growth on the orange line, and here is exponential growth on the blue line. You can see how much bigger it is. And in fact, if we took this out much farther, the exponential growth we'd have to make it so that these geometric growth curves and the linear growth curves would pretty much blend. You wouldn't even be able to tell that they were different just by how much bigger it is. Okay, so we've done our comparison. We've looked at these growth models. Let's talk a little bit about logs for a second. So logarithms play an important role when we're talking about exponential growth. And to do that, I've taken this y equals 2 to the x, this exponential growth function, out further, right? And you can see that somewhere around, let's see, 16, 17, 18, right around the 18th interval here, you start to be able to tell that it's growing. But up until then, right, definitely up until x equals 16, you really can't tell what's going on. And so you don't often see these exponential growth curves graphed out like this. And this is where log scales come in. So logs are the inverse of the exponential function. You can kind of think about it that way. So in a logarithmic form, you have log b of m equals x. And in the exponential form, you have b of x equals m. You can see where these numbers kind of go. So if we go back here and we're looking at this graph, and we took a log of all the numbers, the log base 2, right, of all of these numbers, then what you'd end up seeing is a straight line because we get the x values back and we get a 1-to-1 correlation. It's not really that big of a deal. There's no revelation here. It's just to prove, right, that those are inverse functions. But this is not the best way to kind of look at it, although it does show you kind of how this works. The way that we usually do it is we change the y-axis. So what happens if we change the y-axis to a log scale? Like, what does that look like? And here we've done that for y equals 2x, and I've done a logarithmic scale base 2, because that's what we've got going on here. and we get this nice straight line, and that's because these numbers on the y-axis are logarithmic. That is, from this tick, from 1 to this next tick here, we increase by 3. But if you look, say, from this tick to this tick, which is the same distance, we increase by almost 3,000, right? So it's logarithmic. That's what we mean by that. And if we do this, we can actually now tell what's going on. Remember before, when this wasn't logarithmic, this was basically a flat line, and then somewhere around here it started to go up. Now, this is way too pretty, right? And this is not what we see in real life. If we saw a more realistic graph, then again here in our more realistic graph, we have a log scale, base 10 in this case, and we have this kind of lag phase where we're in exponential growth. Then we get into exponential growth, and then we have this kind of plateau and then a death phase. And the most common way that we talk about, or one of the most common examples, I should say, with logarithmic growth is bacterial growth. And so you'll see these kind of ideas talked about there. So now that we have this idea of a logarithmic scale and exponential growth, let's look at an example. So let's pretend that we're investigators and we're given some data, and here are some dates, and here are cases. And this is actual data from Morris County in New Jersey of the cases of COVID that we're seeing there. And we're asked, like, what does this mean? What's going on? And so we are going to graph this, right? Because we've been looking at graphs and we think, well, maybe that can help us see what's going on. And we see that, yeah, it's kind of flat, starts growing, kind of grows faster. Maybe it could be logarithmic. It's not perfect like we saw with some of our other graphs, but what's happening? So what we can do is we can do what we did before. We can make the y-axis logarithmic, and we can put some reference lines in there too, right? This blue line is our actual data, and we've put it into a logarithmic scale here. I did base 2 again. And this reference line is if the cases doubled every day. This orange reference line is if it doubled every 2 days, and this gray line down here is if we had a doubling of cases every 5 days. What you can see is that in the beginning, like say right in here in March, it looked like it was somewhere, the angle, the slope of the line was pretty close to doubling every day. And then it kind of started flattening out. And then you can kind of go back in history and recent history, you can see when these orders were put in to tell people to stay home, and you can see those started to take effect. They started flattening out the curve, right? And maybe we're doubling every 5 days, right? If you look at the angle of that curve and you compare to these reference lines that we've put in there. Now, I will kind of, and this is not a bad way to kind of look at this growth, because it's tough, right? Because the growth is changing. Maybe it was every day here, every 2 days over here, every 5 days over here. So you can't. It's if you want to actually model it, it's pretty complex, as you can see. So I'll just finish by talking about how I got these reference points. And it turns out that with some help from calculus and differential equations, we can get the formula n of t equals n0 times 2 raised to the t over td. Now, what do these mean? Nt is the number of cases at time t equals the n0, which is the number of cases we had at time 0, which was the first day, times 2 raised to t over td. This is the time interval that we're at, the day that we're at, divided by the doubling time. All right. So if you think about this, then here's our first number of cases was 4. Right. So we would put 4 in here, and then we would do 2 to the t. And let's say it was day 0, the 0th day, you put a 0 here. And let's say we were doing doubling every 5 days, it'd be 0 over 5, which would be 0. 2 to the 0 is 1. 1 times 4 is 4, right? And then on day 1, we'd have 1 over 5, and it'd be the 2 to the 1/5. And you would do 2 to the 1/5 times 4. And you can do that at math if you want, or you can kind of look here and see that it's 4, or it's like 5 or so, right? But that's going to take 5 days to get to 8. So that's how that equation works. This does lead us, this is the same way that we get the famous equation that a lot of people are probably, who know about this, are thinking of, which is nt equals n naught times e to the rt, right? And e is a whole nother story that we could talk about. And of course, we can't go into differential equations, calculus, and natural logarithms in this one little tiny course. But we can use this data, and we can use modeling techniques combined with big data to figure out what might happen in the future. And this is a huge collaboration because we need expertise from epidemiology, statistics, calculus, psychology, for human behavior, computer scientists, to have it all come together to try to model what's happening. So this is intensely complicated. The math, some of the basic math is pretty simple, but it gets very complicated when you really try to figure out what's happening in the real world. There is some more stuff that's going on, and there's some things like logistic regression that we didn't touch on. And you can see that if you go look at some of the models on websites today, that they do go up and it looks exponential, but then it starts to flatten out. And this is called a logistic curve. And those come into play. There's the idea of R naught that we didn't talk about. Human behavior has a whole bunch of stuff we could talk about. And then, of course, the math that we have to use to get these equations. Here's some equations from an actual model that was trying to model exponential growth models in here. So you can see, oh, wow, we're doing very, very simple stuff in this little crash course. And I might try to delve into some of these later, depending on how much time I have. But for now, hopefully suffices. I do want to move on to some medical stuff that I wanted to talk about. But we did give, I think, hopefully a good overview. Talked a little bit about logs, did some investigative work with some actual data, and talked about what could come in the future. So thanks for watching.